Okay, we're given this circuit. We want to find two things. The equivalent impedance seen by the source, which means we're going to need to convert the capacitor and the inductor into their equivalent impedances. Resistances are the same as impedance values, so those will still be the same in the frequency domain. And then we want to find I of t, the current out of the source, for this sinusoidal input. So for a sinusoidal input, I, as t goes to infinity, is also going to be a sinusoid with the same frequency. We just have to find the magnitude and the phase of I of t. That's definitely a frequency domain problem. So we can use our results from part A to find I of t. At any rate, the first thing we need to do is convert the capacitor and the inductor to the frequency domain. The impedance for a capacitor is minus j over omega times c, so that's minus j over omega is 2 radians per second. The capacitance is 1 over 8 farads, so this becomes minus j4 ohms. The inductor's impedance is going to be j times omega times L, which is going to be j times omega is still 2 radians per second. L is 2 henries, so this becomes j4 ohms. Now that we've got our impedances, I'm going to go to a new slide which has the impedances in the place of these elements' values. Okay, here's our frequency domain circuit. The first thing we want is the equivalent impedance seen by the source, so we're looking for what we would normally think of as an equivalent resistance early in the course seen across these terminals. So it's a voltage-current relationship in the frequency domain between these terminals. As with finding equivalent resistances, equivalent impedances can be in series or parallel. So I have two impedances here in series. The equivalent impedance will just be the sum of these two, so this becomes 8 plus j4 ohms. This impedance is in parallel with this negative j4 impedance, so the equivalent impedance of this side of this circuit is going to be the product of the two, so minus j4 times 8 plus j4 over the sum of the two, which is minus j4 plus 8 plus j4. The j4's in this denominator cancel, which make the problem really easy to do even in rectangular coordinates, although normally I do division in polar coordinates. So this becomes minus j4 times 8, which is going to be minus j32, plus j4 times j4 is going to be negative 16 with a minus sign, so plus 16 ohms over 8. So this becomes 2 minus j4 ohms. Now finally, this circuit, if we reduce it, turns out to be plus minus 4 at an angle of 30 degrees. Now I have 2 ohms, and I have this equivalent impedance over here, which is 2 minus j4 ohms. This 2 ohm resistor is now in series with this resistance, so the equivalent impedance is just going to be 2 plus 2 minus j4, which is 4 minus j4 ohms. So there's our answer for part A. Now we want this current as t goes to infinity, so this current phasor is going to be the voltage for at an angle of 30 degrees over the equivalent impedance, which is 4 minus j4 ohms. So that becomes, now definitely this is going to be easier in polar coordinates, so this is 4 at an angle of 30 degrees. The magnitude's going to be 4 square root of 2 at an angle of minus 45 degrees, which becomes, let's see, the 4's cancel. 1 over square root of 2 is a magnitude, and 30 minus a minus 45 is positive 70 degrees. So we need I of t. This is a phasor. That's not our final solution. So I, as t goes to infinity, is a sinusoid with this magnitude, 1 over root 2. Cosine of the frequency was originally 2 radians per second, plus 70 degrees. And there's an answer to our problem. As usual, there's more than one way to do a problem. If I want to find I as t goes to infinity once I'm in the frequency domain, I can use any of the approaches I used with purely resistive networks. Nodal analysis, mesh analysis, circuit reduction, which is what I did here, Thevenin's theorem, etc., etc. So just for fun, let's go ahead and find I as t goes to infinity using an alternate approach. Let's try mesh analysis. So our frequency domain circuit is the same as we started out with before. If I decide to use mesh analysis, I have two mesh loops. So I'll call this mesh loop 1, which, since it's in the frequency domain, is going to be a phasor, I1, and mesh loop 2, which is going to be a phasor, I2. Now just apply mesh analysis the way you ordinarily would, just use impedances where you would use resistances before and use phasors where you'd use current values. So starting down here, so KVL around loop 1, so following I1, I have minus 4 at an angle of 30 degrees plus 2 ohms times its current as a phasor is I1 plus a negative J4 ohms times I1 minus I2. That brings me back to my starting point, so that's 0. So now KVL around loop 2, if I start down here, I have a minus J4 ohms times the sum of the mesh currents, which is going to be I2 minus I1. If I use the mesh current that I'm following for my sign convention, plus 8 ohms times just I2 is the only current going through that element, plus J4 ohms times just current I2 goes through that element. And now solving for I, the only mesh current through this 2 ohm resistor is I1, so the current we're looking for, I, is just the same as I1. So it's probably going to be easiest if I solve these two equations for I1 and then just use that as my answer. So let's rearrange this equation. So loop 2 becomes I2 times a minus J4 ohms plus 8 plus J4 ohms plus minus J4 ohms times a minus I1 is going to be plus J4 times I1. That equals 0. If I solve this, then I2 is going to be minus J4 times I1 over these J4s cancel, 8, so I2 is going to be, let's see, that's 1/2 minus J over 2 times I1. Now we can plug this in for I2 in this first equation. So 4 at an angle of 30 degrees plus 2I1 minus J4 times I1 minus a minus J over 2 I1 is equal to 0. So grouping my I1 terms, I1 times 2 minus J4, so minus J4 times J over 2, J times J is going to be -1, -1 is 1/2, so this is going to be 4 over 2, so that's 2 is equal to, and I forgot a negative sign up here, 4 angle 30 degrees. So I1 is going to be 4 at an angle of 30 degrees over 4 minus J4 ohms, which is 4 at an angle of 30 degrees over 4 square root 2 at an angle of minus 45 degrees. So I1 is equal to I, which is equal to, the 4's cancel, 1 over root 2 at an angle of 30 minus a minus 45 is plus 70 degrees. That's the same answer we got before. So I, as t goes to infinity, is 1 over root 2 cosine of 2t plus 70 degrees. And luckily the answer we get doesn't really depend upon the analysis choice we use. This is probably a bit more work than circuit reduction, but not a lot.